Hello everyone, my name is Cristian Galleguillos and I will present you a joint work with Zeynep, Kiziltan and Ricardo Soto entitled A Job Dispatcher for Large and Heterogeneous HPC System Running Model Applications. High-performance computer systems have been designed to assist researchers to construct, analyze, and interpret complex data. For example, they can be used for weather prediction simulations and seismic simulations. An HPC system has interconnected computational resources that allow to execute programs which traditional computers cannot do or take a lot of time to do. Although current systems are very fast, there is still a need for more computing power to solve the most important and complex challenge in the world. To achieve this, HPC systems are required to reach at least 1 exaflop performance. Currently, to reach this performance, HPC systems are becoming large in size. However, this implies a major electrical power consumption, so in alternative to the CPU power, systems are becoming more heterogeneous in their computer resource, using coprocessors that give a good computational power and consume less electrical power. In the figures, we can see the HPC system of the top 500 list of the fastest system in the world, and 2 systems used in our experimental study. 80% of the system have more than 10,000 CPU cores, 63% more than 1,000 nodes. 30% have heterogeneous computer resource. HPC user request computer resource to execute their program and give other information such as the name of the program and maximum duration. All this data plus the program to execute is known as a job. Assign the job to the system resource correspond to the online job scheduling and resource allocation problem, or the online job dispatching problem, which is solved by a job dispatcher. Since the problem is online, a job dispatcher periodically solves the problem, and on each call, it decides which job to run of those which are waiting in the queue and on which resource to run them. The dispatching decision directly affects the efficiency and the quality of service of the systems. Most dispatchers are based on safe heuristic. First come, first serve, short job first, and backfilling. These traditional job dispatchers have been designed on queue-based approach to execute programs that require days to complete. However, currently this system has a wide range of types of application, not just complex and thick physics simulations, also data visualization or data preprocessing. The new workloads are mainly composed with short jobs with duration up to 1 hour. The figure shows 10 systems with different job duration, and at least 65% of each workload correspond to short jobs. CP-based dispatcher for modern applications has been already proposed in literature. There are 2 types of dispatcher. Pure CP-based dispatcher from CP19, based on a previous work from CP14, which cannot scale well on big systems, because their model increases proportionally to the number of nodes and the possible allocation of jobs. Hybrid CP-based dispatcher for CP19, based also in a previous work, but from CP15, which scale well on big systems due to the model relaxation, by just considering only the scheduling problem in the CP model. This dispatcher really suits for homogeneous systems, that this system with identical resource configuration among nodes without a scarce computer resource on a specific node, such as having GPUs or MIC. Therefore, this dispatcher are not in line with the current trend of systems that is being large and have heterogeneous architectures. So our contribution are a novel CP-based job dispatcher suitable for large and heterogeneous systems, which solves the entire dispatching problem using CP to tackle the scheduling and allocation problem jointly, so computer resources are assigned in an efficient way, especially for heterogeneous systems. To do so, we propose a new allocation model where the number of variables is system size independent. Therefore, we can scale to large systems. Tackle this new trend of large and heterogeneous systems using complete method for optimization is a new application domain of CP. The presentation continues as follows: an introduction to the online job dispatching problem in HPC system, a presentation of the related work that is the state-of-the-art CP-based dispatcher for modern application, the presentation of our proposal, and in specific its new allocation model, then the experimental study and results, and finally conclusions. In the problem, each job has the following parameters: queue time, which is the time when the job was sent to the queue. This value is useful to calculate how long the job is waiting in the queue. The expected duration, that is the time that the job is expected to run. Number of requested nodes define how many nodes will be used for the program, also called jobs units. Number of requested resources of a type which are required by the program to run. And we have some parameters from the system, like node identification, resource type that job can use on each node, capacity of the specific resource type, and the total capacity of a resource. Let's consider the following example to understand how the program represents a typical functioning of a system. There are two jobs at the same time T in the queue, and the system is empty for a resource R1. Both jobs require one node and 1 and 3 units of R1. Using a first fit allocation approach, both jobs are allocated on job 1. At time T plus 1, a new job arrives to the queue. This job requires 3 nodes and 4 R1 resources per node. Using the same allocation approach, the last job will use all the remaining available resources. At T plus 4, the second job finished and a new job arrived into the queue. These new jobs require 1 node and 4 units of R1. Since this job cannot fit in the system at current time, this job is maintained in the queue until it can be dispatched. And that is how the problem evolves during the time on an HPC system. Obviously, with more number of types of resource and more resource, and receive every time more jobs during the time. Now I will introduce the state-of-the-art CP-based dispatcher for modern application. The first dispatcher is something that we call PCP19 from CP19. This dispatcher is based on PCP from PCP14, and it uses a single model for the dispatching problem. The experimental and production results showed better results than priority rules-based dispatcher, which are commonly used in commercial workload management systems. However, this dispatcher presents an issue. The model size grows proportionally to the system size. The scheduling part is not a problem because it uses only one condition interval per job. The problem is in the resource allocation part, where each scheduling variable is replicated p times for each node to model all possible allocation, where p is the minimum between the requested nodes and the maximum number of times a job fits on each node. Using this resource allocation model, a serial job which requires only one node on a big system, for instance, n equal to 1000, will be modeled using 1001 variables. Therefore, this dispatcher is not suitable for large systems due to the high demand of memory to support its execution and the required time to find a solution. The second dispatcher is HCP19 from CP19 and based on HCP from CP15. This dispatcher was initially proposed to tackle the model size issue. As its name says, this is a hybrid model with two solving steps. The scheduling part is model and solved using CP. The allocation part is solved using a heuristic search based on best fit to reduce the fragmentation on the system usage. This dispatcher presents a good performance on homogeneous architecture. And also the dispatcher presents a better solution than PRB dispatcher that are priority rules-based dispatchers. However, this scheduling model does not take into account the nodes resource compositions, which make it infeasible schedule, which are later fixed by the allocation heuristic, causing the dispatcher to iterate several times between the scheduling and allocation in an heterogeneous system, which present a more complex architecture. Therefore, the dispatcher performance may be degraded on a system with an heterogeneous architecture and workloads. For PCP21, we maintain the scheduling model from PCP19 and propose a new allocation model. We consider all the resources of a certain type in an ordered array by following the sequence of the nodes. As shown in the figure, which represents a system with 4 nodes, and each color in the array shows the corresponding node. The numbers on each box are the position in the array. Let's consider the following example of the table where job 1 can be a running job, and it's using one node and requesting 3 units of memory, 1 unit of GPU, and 1 unit of core. In this example, we use a Y variable to model the first position in the structured array that will be assigned for a job unit J for a resource R. All these resources should be placed on the same node. In this case, correspond to node 1. It's important to notice that running jobs are already occupying a resource, so we always place them at the most minimal available position. Let's consider the remaining jobs. Job 2 requires 1 node and 2 GPUs, so the only valid option to allocate the job is in node 2. Job 3, which is a parallel job because it requires 2 nodes, it requires 2 entire nodes because it's requesting 4 cores for each node, so it can be placed only on node 3 and node 4. Job 4 requires 1 unit of MIC. However, the nodes that have these resource types are node 3 and node 4 that are already occupied by job 3. So this job must be postponed. So we model the position of a job unit for a specific resource type using the wait variables. We also need to represent time during which the allocation is valid. Then we use a 2-dimensional box to model an allocation in time. The y-axis gives the position of the allocated resource, and the x-axis gives the time interval which the resource is consumed. The vertices of the box are defined by the variables in the origin, starting time and the starting position in the allocation. The box expands from the origin by the expected duration in the x-axis, instead in the y-axis by the required resource amount. To enforce that the resource is used by only one job unit, we forbid the boxes to overlap using the defend constraint for each resource type. As the domain size of the resource position variables depend on the system size and can be large, we add an implied constraint to shrink them. They are the classical cumulative constraint used together with defend constraint in packing problems. Given that the job unit for parallel job have identical resource requests, their reallocation are symmetric. We post an ordering constraint on the position of the job units of a job I on a resource type R to break symmetry. It is a strict ordering as the position variable takes different values. We need additional constraint to guarantee that certain allocations are in the same node. For that, we use a mapping array for each resource type, which is based on the system representation introduced earlier. But with the content of the array is the number of the corresponding node. To ensure that the resource of different type of a job unit must be allocated in the same node, we post an element constraint. R hat is the subset of resource types which consider only the requested resource of the job I. We also use the element constraints to enforce the allocation of single resource spans in the same nodes. We use a custom search derived from the schedule and postpone algorithm to search on the scheduling variables. At each decision node, we select the job with the highest priority and can start first. Priority are calculated once statically at dispatching time t before the search start. We use the job slowdown as priority, which is the normalization of the waiting time. Next, we assign the scheduling variable of the selected job. Its minimum time is the earliest starting time. Then we search on the allocation variable of that job. We start with the resource which has the lowest availability at time t. Then we select on them in lexicographical order and assign them their minimum value. This guarantees consistency with the symmetry breaking constraint on the allocation variable. A job unit can be allocated on all nodes if all nodes in the system have the requested resource. This typically occurs when only cores and memory are requested. We call this an homogeneous workload. So here we adapt the search algorithm to break symmetry. And after a resource allocation for a job, if the search fails or want to find a better solution, it backtracks to the scheduling variable, as opposed to backtracking to the allocation variable. This search is bound by a time limit with the problem complexity. To evaluate the significance of our approach, we conduct an experimental study by simulating an online job submission to two HPC systems. We try to find answers to the following questions. How do PCP19, HCP19, and PCP21 compare when they are engaged in a workload with heterogeneous resource request? Can PCP19 and PCP21 scale to a large system? As we said earlier, an heterogeneous system may also receive a workload with homogeneous resource request. So we also formulate the following question. How much do we lose by using PCP21 for a workload with homogeneous resource requests compared to HCP, which is more suitable for homogeneous systems? Our study is based on two different workload traces collected from two different HPC systems. The first system is Aurora. It's a small system compared to the current trend, but the architecture is heterogeneous. The dataset consists of over 400,000 jobs submitted during 1 year and is dominated mainly by short jobs. In the model, we use the estimated job duration. For Aurora, we use the data-driven heuristic prediction called D and the real duration as a baseline that we call R. The other system is KIT, which is a big system with more than 1,000 nodes. The workload is composed of more than 100,000 jobs and has homogeneous resource requests. The workload is also dominated by short jobs. As expected job duration, we use the last two methods and the real duration. We simulate both systems using the Akasync workload management simulator. Now let's check the result of Aurora. We evaluate two aspects: the performance by comparing the average dispatching time and the total simulation time that appears in the table, and the quality of service by comparing the slowdown and the waiting time. All the dispatchers complete the simulation of Aurora. Comparing the performance in the table, we can clearly see the benefits of using PCP21. The performance dropped almost the half when using D with respect to HCP19. The average of dispatching time is still less compared with PCP19, which could be attributed to its higher number of decision variables. PCP21 is the most efficient dispatcher also when using R. In the quality of service figures, we also compare to the original Aurora dispatcher called PBS, and we can observe that all dispatchers generate better solutions. Among CP-based dispatcher, PCP results in the best average slowdown when using D. On R, the dispatcher have low slowdown values and have similar waiting times. This figure shows the ratio of the number of decision variables between PCP29 and PCP19 versus the percentage of the instance. Each instance was obtained from the simulation of PCP19, which later were simulated individually with PCP21. For all instances, the ratio is below 0.1, providing a significance of the new allocation model. Here the figure shows the ratio of the dispatching time versus the ratio of the number of fails for each individual instance. Almost 90% of the instances fall in the region where both ratios are between 0 and 1 when using D and R. Summarizing on Aurora with the heterogeneous resource request dominated by short job, PCP21 is more efficient than HCP19 and PCP19. PCP21 reduced significantly the number of decision variables compared to PCP19. The dispatching time and number of fails are also reduced significantly. Now let's see the result of the simulation on KIT. As we expect, PCP19 cannot complete the simulation. Instead, PCP21 and PCP21S complete the simulation, and in the table, this confirms the advantage to the PCP19 in a large system. We can also observe that the symmetry breaking is crucial with an homogeneous workload. PCP21S significantly reduced the total simulation time and the average dispatching time compared to PCP21. The performance on PCP21S is not too far from that performance achieved by HCP19. The gap is around 20%. You can see in the figure that in terms of quality of service, the dispatcher behaved almost identically. Summarizing on KIT with homogeneous resource requests dominated by short jobs, we improve the search on homogeneous workloads by breaking the symmetry among identical resources, reducing the performance difference with HCP19. In general, the results provided evidence that the proposed dispatcher performs well in large and heterogeneous systems running modern applications. We discussed the limitation of the available CP-based job dispatcher that may hinder their practical use in today's systems that are becoming larger in size and more heterogeneous in their computer resource. In an attempt to bring CP closer to a deployed application, we presented a new job dispatcher for HPC system that we call PCP21. Unlike its predecessors, CP21 solves the entire problem using CP, and its model is independent of the system size. The experimental result based on a simulation study showed that our approach can bring about significant performance gains over the existing dispatcher in a large or heterogeneous system.